Let's look at another example of where Taylor series or Maclaurin series might be useful. Suppose we have a velocity function of the form 1 over 1 plus t to the 7. So perhaps a particle moving in a straight line has a velocity 1 over 1 plus t to the 7. Then we know from Calc 1 that the displacement at time t1 is the integral from 0 to t1 of this velocity function with respect to t. And now we know that the way to go about this, or the formal way to go about integrating this function, is to use partial fractions. And this is rather difficult because it's a 7th degree polynomial in the denominator. So here we have a picture of the velocity, and of course the displacement at time t1 is the area under this curve between 0 and t1. An easier way to approach this would be to approximate this function 1 over 1 plus t to the 7 by a polynomial on our interval of interest, and then to integrate the polynomial. Now, of course, the Maclaurin series for this function we can find by substitution using our expression for the geometric series. And we can take the 10th Taylor polynomial, or the 10th Maclaurin polynomial here, and of course the only non-constant term there is minus t to the 7. So the 10th Maclaurin polynomial is 1 minus t to the 7, and this is a reasonable approximation to the function 1 over 1 plus t to the 7 in some interval around 0. And we can get an idea from the graph how good an approximation that is. For our 10th degree Taylor polynomial, it's shown in red here, and the graph of the velocity function is shown in blue here. And we see this is a pretty good approximation up to perhaps 0.7 here, maybe 0.8. If I wanted to find the displacement of this particle after, for example, 0.7 seconds, then the integral from 0 to 7 of 1 minus t to the 7 would be a pretty good approximation. Now, if I wanted to get a good approximation to the distance that the particle had traveled after t1 equals 1 second, say, let's assume t is measured in seconds here, then I could increase the degree of the Taylor polynomial I use. And of course, this is nice because I have a picture of what's going on, but we'll see how to control this error later without graphs using algebra in the lecture. So certainly the Taylor polynomial of degree 60 is a pretty good approximation to the graph of 1 over 1 plus t to the 7 on the interval from 0 to 1. So if I generate that Taylor polynomial with Mathematica, then I see that it doesn't really have 60 terms. It really just has 9 non-zero terms. So in fact, it's pretty easy to integrate. And when I integrate this polynomial between 0 and 1, I get 0.923717. And the actual area under the curve, or the actual displacement on that interval, is 0.91548. So we have a pretty good approximation to the displacement here on the interval from 0 to 1. Now, if I used a smaller polynomial, you can see that the error would be larger. So let's use the 10th degree Taylor polynomial here to approximate the displacement of this particle between 0 and 1, and my approximation is 0.875. And the real displacement is given here as 0.91548, so this is not such a good approximation as using the 60th degree Taylor polynomial.